this module, we will be studying about electric charge. Sometimes, if you touch any metallic object, you might experience a mild shock. This is because the metallic object carried an electric charge. Objects that carry an electric charge are said to be electrically charged. Also, you must have observed that when a comb is rubbed against dry hair, it begins to attract small pieces of paper. When two pieces of silk cloth are rubbed against glass rod individually, and the glass rods are kept beside each other, the glass rods repel each other. Now, if one of the silk cloth and a glass rod are kept beside each other, they attract each other. Now, bring one charged glass rod in contact with a pith ball and then separate them. Then, bring the other charged glass rod in contact with the other pith ball and then separate them too. When these pith balls are kept close to each other without contact, we observe that they repel each other. The physical quantity responsible for all this phenomena is known as electric charge. Electric charge can be defined as the property of matter that exhibits its electrostatic interaction with other matter. Looking at the earlier examples, we can conclude that bodies like combs, glass rod, silk cloth pieces, pith balls, etc. are said to be electrified or are called charged bodies. The study of electric charges at rest and the physical quantities associated with electric charges at rest is called electrostatic or static electricity. These experiments prove that the body can be charged by rubbing against another body or by simply bringing a charged body in contact with another uncharged or neutral body. When the glass rod and silk cloth were first rubbed, they get electrified. But when they are brought in contact again and separated, they lose their electrification of charge and are neutralized. In other words, the charge on them is nullified. Hence, we can conclude that one of them may be positively charged and the other negatively charged when they are rubbed against each other. From these observations, we see that there exist only two types of electric charges in the nature. These are called positive and negative. It is also observed that the like-charged bodies repel each other. For example, two pith balls, both carrying like charges, repel each other, unlike charged bodies that attract each other. For example, a pith ball carrying a positive charge will attract a negatively charged pith ball. Let us now understand this phenomenon at an atomic level. We know that all matter is made up of atoms or molecules. Within an atom, the total negative charge is balanced by the total positive charge in it. When we rub one material against another material, the material in which electrons are relatively loosely bound to its atoms loses a few of its electrons to the other material. The material that lost electrons now has a deficit electron and hence becomes positively charged, and the one that gained electrons becomes negatively charged. In this case, the glass rod lost electrons and became positively charged, and the silk gained those electrons and became negatively charged. We will be learning about properties of charges. Conventionally, electric charges are called positive and negative charges. Like charges repel each other, and unlike charges attract each other. However, if the size of charged bodies is very small, but the distance between them is comparatively larger than their sizes, then such charged bodies are treated as point charges. Coulomb, C, is the SI unit of electric charge. However, smaller units such as microcoulomb and millicoulomb are also used in electrostatics. Electric charge is a scalar quantity which has only magnitude but no direction. Hence, the total charge on the body is equal to the algebraic sum of the individual charges given to it. Let us illustrate this with an example. Consider a body carrying a charge Q1, and we add another charge Q2 to this body. Now, the total charge on the body is the algebraic sum of both charges. That is, total charge Q is equal to Q1 plus Q2. Similarly, if a body carries n number of charges, Q1, Q2, and so on up to Qn, then the total charge on the body Q is equal to Q1 plus Q2 plus Q3 and so on. It is important to note that while adding the charges, proper signs should be used. That is, positive sign for a positive charge and a negative sign for a negative charge. We can determine whether a body is charged positively or negatively by finding the algebraic sum of all charges on the body. For example, if a body is given 5 charges all in Coulomb, say +1, -2, -3, -4, +5 is equal to -3C, which means it is a negatively charged body. Another property of electric charges is that the total charge in an isolated system is always conserved. When a glass rod is rubbed with a silk cloth, then electrons are transferred from the glass rod to the silk cloth. Now, both the glass rod and the silk cloth are charged. Here, there is only a transfer of charge taking place, and neither is a new charge created, nor is any charge destroyed. The number of electrons lost by the glass rod is equal to the number of electrons gained by the silk cloth. If we consider the glass rod and silk cloth as an isolated system, then the total charge of this system before and after rubbing remains the same. Therefore, we can conclude that the total charge of an isolated system is always conserved. We also find that in the natural process, such as the beta decay of a neutron, the charges are conserved, and during the same, the neutron breaks into proton and electron, releasing a neutrino. Here, the neutron and the neutrino are chargeless particles, while the proton and electron are oppositely charged particles whose combined net charge is 0. Hence, we observe that the total charge in this process is conserved, and the charge on an object is measured in an integral multiple of the basic unit of charge that the proton or electron carries and is denoted by E. This property is called quantization of charge. The magnitude of the basic unit of charge E is 1.6 into 10 raised to the power 19 coulomb. In an atom, when we refer to the charge on proton, its value is positive and is referred to as positive E, whereas the value of E for the charge on an electron is negative and is referred to as negative E. Thus, the charge on an object Q is equal to the product of the number of electrons gained or lost by it, N, and the basic unit of charge, E. Now let us calculate the number of electrons 1 coulomb of negative charge carries. Consider a body possessing a charge Q is equal to minus 1C. Let the number of electrons it has gained to become negatively charged by N, and as the charge Q is quantized, we have Q is equal to Ne, where the basic unit of charge has a magnitude of 1.6 into 10 raised to the power 19 coulomb, and Q is equal to minus 1C. Substituting the values of Q and E and simplifying, we have N is equal to minus 6.25 multiplied by 10 raised to the power 18. Here, N is a negative integer, indicating that the body has gained a negative charge. So we see that 1 coulomb of negative charge contains 6.25 multiplied by 10 raised to the power 18 electrons, which is a very large number of electrons. In the practical examples, we have seen, for charging a body, we deal with bodies possessing a charge of few microcoulomb. It is important to note that quantization of charge is significant only in the microscopic sense, when the charge possessed is due to a few hundred times the basic unit of charge E, or even less than that. In this module, we will be learning about Coulomb's law. Coulomb's law states that the electrostatic force between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between the charges. That is, F is directly proportional to the product of Q1 and Q2. Let us label it as equation 1. Also, F is inversely proportional to square of the distance R between the charges. Let us label it as equation 2. Hence, the electrostatic force F between the charges Q1 and Q2, separated by a distance R, is proportional to Q1 Q2 upon R square. Let us label it as equation 3. A constant of proportionality K is used to get the equation F is equal to K Q1 Q2 upon R square. Let us label it as equation 4. If the charge is separated in free space, that is, air or vacuum, the value of constant K is equal to 1 by 4 pi epsilon naught, where epsilon naught is called the permittivity of free space. From equation 1, 2, 3 and 4, the electrostatic force F is equal to 1 by 4 pi epsilon naught Q1 Q2 upon R square. In SI units, the value of the proportionality constant K is approximately equal to 9 into 10 power 9 Newton meter square by Coulomb square, and epsilon naught is equal to 8.85 into 10 power minus 12 Coulomb square by Newton meter square. Hence, F is equal to 9 into 10 power 9 into Q1 Q2 by R square. Using Coulomb's law, a unit charge can be defined as one that experiences an electrostatic force of 9 into 10 power 9 Newton when placed at a distance of 1 meter from another unit charge in free space. Let us now study Coulomb's law in vector form. Let the charges q1 and q2 be at positions specified by the position vectors r1 and r2 with respect to the origin O. The vector r21 is equal to r2 minus r1 and joins q1 and q2. The force on q1 due to q2 is F12. The force on q2 due to q1 is F21. In vector form, we can express Coulomb's law as shown here. If q1 and q2 are like charges, they repel. In this case, the product of the charges q1 and q2 will be positive. The unit vector r12 cap is given as shown. Here, the force F12 will be in the direction of unit vector r12 cap. If q1 and q2 are unlike with respect to each other, the force F12 will be in the direction of unit vector r21, since unlike charges attract each other. In this case, the product of the charges q1 and q2 will be negative. The unit vector r21 cap is given as shown. According to Newton's third law, Q2 experiences an equal and opposite electrostatic force to the one experienced by Q1. Therefore, we can write F21 is equal to minus F12. This module, we will be studying about electric field. Consider a charged particle with a charge q held at rest at the origin of an imaginary coordinate system. If we place a charge q0 at a point n near charge q and release it, then the charge q0 accelerates away from the origin. This acceleration is due to a force on charge q0. Now, let us remove the charge q from the origin and reintroduce charge k0 at the same point n. Charge q0 does not accelerate now and remains at rest. This means that the force experienced by q0 is due to charge q. We say that since charge q0 is in the electric field of charge q, it experienced a force. An electric field is the region in which the influence of a charge is felt. We can use Coulomb's law for calculating the force on q0 due to q. The electrostatic force on q0 due to charge q is F is equal to 1 by 4 pi epsilon naught q0 by r square into r cap, where r cap is unit vector along the direction of ON. Let us label it as equation 1. Now, if q0 is a unit positive charge, that is, q0 equal plus 1 coulomb, then the electrostatic force as denoted by equation 1 will be 1 by 4 pi epsilon naught q by r square into r cap. Let us label it as equation 2. Equation 2 indicates the electric field strength or intensity of electric field E, which is the force on a unit charge acting at a particular point in the electric field. Therefore, the electric field strength due to charge q at point n is E is equal to 1 by 4 pi epsilon naught q by r square into r cap. Let us label it as equation 3. Electric field strength E is a vector quantity pointing in the direction of the force on a unit positive charge at a point in the electric field. In SI units, it is measured in Newton per coulomb or volt per meter. From equations 1 and 3, the force on the charge q0 can now be expressed as F is equal to Q naught E. Let us label it as equation 4. Hence we can write the electric field strength at N as E is equal to F by Q naught. Let us label it as equation 5. The above equation is valid as long as the test charge Q naught is very small and its own electric field is negligible. Hence, at point N, we write the electric field strength. E is equal to F by Q naught limit, Q naught tending to 0. For a given distance r from a source charge Q, the value of 1 by 4 pi epsilon naught is always constant, and hence E as given by equation 3 will also be constant. Hence, the electric field strength E at distance r from the source charge Q is independent of the test charge Q naught and varies with r cap and is inversely proportional to r square. It is important to note that the electric field at any point in the electric field is finite and is 0 only when distance r is equal to infinity. In the electric field of a positively charged particle, the electric field strength vector E at any point of the field always points away from a charged particle in a radially outward direction. The point charge Q naught will be accelerated in the electric field as it experiences acceleration A due to the force due to the electric field, and the acceleration is expressed as A is equal to Q naught E by m. Note here, m is the mass of the particle. In the electric field of a negatively charged particle, the electric field strength vector E at any point of the field always points towards the charged particle in a radially inward direction. Here, the point charge Q naught in this electric field will be accelerated in the direction opposite to the electric field. The magnitude of acceleration Q naught is the same regardless of whether the electric field is due to source charge plus Q or minus Q. It is important to note that for a charge Q at all points on an imaginary sphere of radius r around it, the electric field strength may be equal in magnitude and be equal to 1 by 4 pi epsilon naught Q by r square. There is a spherical symmetry with respect to the magnitude of electric field E with charge Q. In this module, we will be studying about electric field lines. For a point charge plus Q and its electric field, let us introduce a unit positive charge at a point N1 in the electric field of Q. As both the source charge and the test charge are positive, this unit positive charge placed at point N1 follows the path N1A in the electric field due to the repulsive force on it exerted by the electric field of the source charge. Thus, path N1A represents an electric line of force or an electric field line. An electric field line represents the path followed by a unit positive charge in an electric field. Now, if we repeat this procedure for various points in the electric field, we obtain the electric field lines around the charge. Electric field lines are used to represent the electric field of a charge or a system of charges pictorially. In fact, the electric field lines follow the same direction as the electric field vector at any point in the electric field. Since electric field line is the path followed by a unit positive charge in an electric field, If we draw all the electric field lines for the electric field of the given source charge Q, the electric field lines appear as shown. Electric field lines help us estimate the electric field strength. The relative density or closeness of the field lines at different points gives an indication of the relative strength of the electric field at those points. The field strength is stronger at places having more crowded field lines than at places where they are less crowded. To illustrate this, let us now consider two regions, P and Q, of same area placed normal to the field lines in the electric field. The field lines in region P are relatively closer than those in region Q. The number of field lines passing normal to an area is proportional to the magnitude of the electric field strength at these points. This indicates the strength of electric field at P is greater than that at Q. As the electric field strength is stronger at region P than Q, as the field strength varies from region to region. To understand the dependence of field lines on area, let us understand the relation of the area of the element and the solid angle created. It is important to note that solid angle is a measure of a cone. When the intersection of a cone with the sphere of radius r is considered, the solid angle delta omega subtended by the area element is defined as delta s by r square, where delta s is the area in the sphere, which is the area element cut out by the cone. Let us label it as equation 1. Therefore, delta s is equal to r square delta omega. Let us label it as equation 2. For a given solid angle, delta s, the number of radial lines, is the same. At two different points, say A and B in the electric field, which are at distances r1 and r2 from the charge, we had seen that the area of the elements subtending the same solid angle, delta omega, will be delta S1 is equal to r1 square delta omega at A and delta S2 is equal to r2 square delta omega at B, respectively. The number of field lines, say n, passing normal delta S1, delta S2 is also the same. The number of field lines passing normal to a unit area is equal to electric field strength E. Therefore, the electric field strength E1 at A will be equal to the number of field lines per unit area at A, which is equal to n upon delta S1 or n upon r1 square into delta omega by using the value of delta S1. Let us label it as equation 3. Similarly, the electric field strength E2 at B will be equal to n upon delta S square or n upon r2 square into delta omega. Let us label it as equation 4. If we divide equation 3 and 4, we see the ratio of electric field strength at A and B is equal to r2 square upon r1 square. Hence, we can conclude that the electric field strength due to point charge varies inversely to the square of the distance from the charge. From the equations 3 and 4, we see that even though the number of field lines n and solid delta omega are the same at A and B, the electric field strength E, which will be equal to number of field lines per unit area, is proportional to 1 upon r square, where r is the distance of the point from the charge Q. In this module, we will be learning about electric dipole. By definition, a dipole consists of a positive charge and a negative charge separated by a finite distance. Consider a dipole with a positive charge plus q placed at A and negative charge minus q placed at B at a distance of 2a. Thus, distance between the charges is referred to as the length of the dipole. For an electric dipole, the midpoint O of the line joining the dipole is called the center of the dipole, and the straight line passing through the charges and also through the center is called the axis of the dipole. Assume that the dipole is placed such that the center O of the dipole coincides with the origin, and the axis of the dipole coincides with the x-axis of the Cartesian coordinate system. The charge minus q is placed along the positive x-axis, and the charge plus q is placed along the negative x-axis. The product of the length of the dipole and the magnitude of the charge is called the electric dipole movement P. Here, P is equal to 2aq, which is a vector quantity directed from minus q to plus q. Let us now obtain the electric field strength E at point T on the axis of the electric dipole, which is at a distance x from the midpoint O of the dipole. The magnitude of electric field strength E due to a charge q at a distance r from it is given by E is equal to 1 by 4 pi epsilon naught into q by r square. The magnitude of the electric field strength E1 due to the charge plus q is equal to 1 by 4 pi epsilon naught q by x plus a square. Let us label it as equation 1. The direction of this electric field is in the direction opposite to that of dipole moment. The magnitude of the electric field strength E2 due to the charge minus q is equal to 1 by 4 pi epsilon naught q by x minus a square. Let us label it as equation 2. The direction of this electric field is in the direction of the dipole moment. Point T is nearer to the charge minus q than the charge plus q. As the distance of the point P from minus q is lesser than that from plus q, the magnitude of the electric field strength E2 is greater than E1. Hence, the magnitude of the resultant electric field strength E at the point T is equal to E2 minus E1. Let us label this as equation 3. The direction of the resultant field strength at the point is in direction of E2. Substituting the value of E2 and E1 and simplifying, we get the expression for the electric field strength E as 1 by 4 pi epsilon naught or qx by x square minus a square whole square. Let us label it as equation 4. On further solving the equation 4, we get E is equal to 1 by 4 pi epsilon naught 2x into 2aq by x square minus a square whole square. Please note that in this equation, 2aq is the magnitude of the dipole moment P. Therefore, E is equal to 1 by 4 pi epsilon naught 2px by x square minus a square whole square. Let us label this as equation 5. When the point T is at a very large distance from center O, then x is very large compared to point A. Then, writing the expression 5 as an equation 6 and neglecting the term a square by x square for x, which is very large as compared to a in equation 6, and on further simplification, we get E is equal to 1 by 4 pi epsilon naught 2px by x power 4. Let us label it as equation 7. This can be further simplified as E is equal to 1 by 4 pi epsilon naught 2p by x cube. Let us label it as equation 8. Equation 8 can be expressed as 1 by 4 pi epsilon naught 2p by x cube into p cap, where p cap is the unit vector along the dipole axis in the direction of minus q to plus q. Let us label it as equation 9. Let us now obtain an expression for the electric field strength E at point F on the axis on the equatorial plane of electric dipole. Let point F be at a distance y from the center of the dipole. The point F is at a distance r and is equal to root y square plus a square from each charge of the electric dipole. Let us label it as equation 10. At the point F, the positive charge creates an electric field of magnitude. E1 is equal to 1 by 4 pi epsilon naught q by r square. Let us label it as equation 11. Electric field strength E1 is directed away from the positive charge and acts along the line joining the charge plus q and point F as shown. Similarly, the negative charge creates an electric field of magnitude. E2 is equal to 1 by 4 pi epsilon naught q by r square. Let us label it as equation 12. Electric field strength E2 is directed towards the negative charge and acts along the line joining the point F and the charge minus q as shown. We observe that the magnitude of E1 is equal to that of E2. The point F lies on the perpendicular bisector of the line joining the charges plus q and minus q. Hence, by geometry of the triangle FAB, the angle FAO is equal to the angle FBO. Let this angle be theta. Now, the angle E1 FE2 is the exterior angle of the triangle FAB and hence is equal to 2 theta. The resultant of E1 and E2 is obtained by using the parallelogram rule for vector addition. According to the rule, the resultant of E1 and E2 is obtained by diagonal of the parallelogram formed by the vectors E1 and E2 as the sides. Since the magnitudes of E1 and E2 are equal, the lengths of the vectors representing E1 and E2 are also equal. Hence, the diagonal of the parallelogram formed by the vectors E1 and E2 as sides bisects the angle 2 theta. Thus, the resultant of E1 and E2 makes an angle theta with the direction of both E1 and E2. The resultant of E1 and E2 is parallel to the x-axis and is directed along AB. Let us consider the components of E1 and E2 along the x and y axes to find the magnitude of the resultant electric field at the point F. The components of the electric field E1 along the x and y axes are E1x and E1y respectively as shown. And the components of the electric field E2 along the x and y axes are E2x and E2y respectively as shown. Since the electric field strengths E1 and E2 are of equal magnitude, the components E1x and E2x will be equal. Similarly, E1y and E2y will be equal. We also observe that the components E1y and E2y are oppositely directed and so cancel each other. Therefore, at the point F, the resultant electric field strength E is equal to E1x plus E2x. Let us label it as equation 13. As the angle between E1 and x-axis is theta, the component E1x is equal to E1 cos theta. Substituting the magnitude of E1, we get E1x is equal to 1 by 4 pi epsilon naught into q cos theta by r square. Let us label it as equation 14. Similarly, the angle between E2 and x-axis is theta, and hence the component E2x is equal to E2 cos theta. Substituting the magnitude of E2, we get E2x is equal to 1 by 4 pi epsilon naught into q cos theta by r square. Let us label it as equation 15. Substituting equations 14 and 15 in equation 13 and simplifying, we get the magnitude of the electric field at point F. E is equal to 1 by 4 pi epsilon naught into 2q cos theta by y square plus a square. Let us label it as equation 16. From trigonometry of either of the triangles FAO or FBO, we get cos theta is equal to a by r. Substituting the value of r, we get cos theta is equal to a by square root of y square plus a square. Let us label it as equation 17. Substituting equation 17 in equation 16 and simplifying, we get the equation for the magnitude of the resultant electric field E at point F. Since the dipole moment T is equal to 2aq, we get E is equal to 1 by 4 pi epsilon naught into p by y square plus whole square, whole power 3 by 2. Let us label it as equation 18. The direction of the electric field strength at the point F is opposite to that of the electric dipole moment and parallel to the axis of the dipole as discussed earlier. When the point F is at a very large distance from the center O, then y is very large as compared to a. Then, writing the expression 18 as in equation 19 and neglecting the term a square by y square for y, which is very large as compared to a in equation 19, and on further simplification, we get E is equal to 1 by 4 pi epsilon naught p by y cube. Let us label it as equation 20. In vector notation, electric field strength E can be expressed as shown in equation 21. The negative sign is used since the electric field strength E is opposite to the direction of the unit vector p cap. For a given dipole, the magnitude of the dipole moment p is constant. From the expression of the dipole moment, we get charge q is equal to p by 2a. Hence, as the length of dipole 2a tends to 0, the magnitude of the charge q tends to infinity, so that the dipole moment p is equal to 2aq becomes finite. We will be studying about continuous charge distribution. Electric fields are produced by continuous charge distribution on the surfaces of the bodies of finite size. A few examples of practical situations are a line charge distribution, a sheet of charge, or a volume charge distribution. Now, to evaluate the electric field at a point due to these charge distributions, we assume the entire charge distribution to be made of infinitesimal small elements, and the electric field strength at any point in the electric field will be equal to the vectorial sum of the electric field strengths due to each such small element. Let us look at the like charge distribution of length L carrying a charge Q as shown. If we consider a small element of such a charge distribution, having a charge delta Q and of length delta L, the linear charge density lambda of such an element is equal to delta Q by delta L. Since it is the charge per unit, the SI unit of linear charge density, lambda, is coulomb per meter. It is a scalar quantity. If a line charge distribution is carrying a non-uniformly distributed charge, then its linear charge density for an individual element is equal to delta Q by delta L. If a conductor of length L is carrying a uniformly distributed charge Q, then its linear charge density is equal to Q by L. Now, let us consider a sheet of charge carrying a total charge Q on a surface area A. In such situations, the electric field strength at an imaginary point P can be calculated by assuming the charge distribution to be divided into infinitesimally small area, each having an area delta A and a charge distribution delta Q. Surface charge density sigma is the charge per unit surface area. Therefore, the surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. It is a scalar quantity measured in coulomb per meter square in SI unit. If the charges are non-uniformly distributed, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. If the charges are uniformly distributed over the surface, then the surface charge density sigma is equal to Q by A. Now, let us consider a volume charge distribution. Consider a volume V carrying a charge Q. Let us assume that the total volume is divided into a number of small elements, each of volume delta V having a charge delta Q. Then, volume charge density or charge density ρ of such a volume charge distribution is defined as the charge per unit volume. Thus, ρ is equal to delta Q by delta V and is measured in coulomb per meter cube in SI unit. It is a scalar quantity. If charges are not uniformly distributed, the charge density ρ for an individual volume element is equal to delta Q by delta V. If the charges are uniformly distributed, the volume charge density of the conductor is expressed as ρ is equal to Q by V. Now, consider the small volume element delta V of charged distribution carrying a charge delta Q. We know that the charge density ρ is equal to delta Q by delta V. Thus, the charge on the volume element is then delta Q is equal to ρ delta V. The position vector of the volume element delta V with respect to the origin O is R. Consider a point T in the electric field of volume charge distribution, which is at a distance of R' from the volume element delta V. The electric field strength at point T due to the volume element is delta E is equal to 1 by 4 pi epsilon naught delta Q by R' square into R' cap, where R' cap is the unit vector in the direction of the straight line from the volume element towards the point T. This can be written as delta E is equal to 1 by 4 pi epsilon naught into rho delta V by R dash square into R dash cap. Now, the electric field strength E at T due to the total volume charge distribution is equal to the vectorial sum of the electric field strengths due to all individual volume elements. Since there will be many infinitesimal volume elements at varying distances from the point T, hence, to obtain the electric field strength E due to the total volume charge distribution, we integrate delta E within suitable limits A to B under the assumption that the volume elements have very small volume tending to zero. This module, we will be studying about the Gauss law. Let us assume a uniform electric field of strength E along the x-axis. Consider a rectangular surface of area A placed in the uniform electric field such that its axis makes an angle theta with the direction of the field. In other words, the area vector A, which is conventionally taken along the outward normal to the surface, makes an angle theta with the direction of the electric field. The electric flux passing normal to this area is then given as phi is equal to E dot A or phi is equal to EA cos theta. Now, consider a closed surface S placed in the uniform electric field of strength E. Consider three elements X, Y, and Z on the closed surface having areas delta A1, delta A2, and delta A3 respectively. The electric flux through the element X is phi1 equal to E dot dA1. And since the angle between the direction of the electric field, strength E, and dA1 is acute, the flux phi1 through the surface is positive. For all such elements, the flux passes from the outside to inside. That is, they have invertly normal flux. Since theta is equal to 90 degrees for element Y, the electric flux for Y is equal to 0. For all such elements, the flux through the surface is 0. Similarly, since theta is obtuse for element Z, the flux through the element is negative. For all such elements, the flux through the surface passes from the inside to the outside. That is, they have an outwardly normal flux. From these observations, we can say that the inwardly normal flux is negative and the outwardly normal flux is positive. Let us now consider a point charge plus Q placed at the center of the sphere of radius r. Let us now look at Gauss' law, which defines the relation between the net electric flux through a closed surface and the charge enclosed by that closed surface. The law is of fundamental importance in the calculation of electric field strengths. The closed surface is referred to as the Gaussian surface. The electric field lines of the point charge plus Q are outwardly normal to the charge and hence are outwardly normal to the sphere at all points on its surface. The magnitude of the electric field E at a distance r from the point charge is equal to 1 by 4 by epsilon naught Q by r square. Let us label it as equation 1. So we see that for all points on the sphere of radius r, the magnitude of the electric field strength is the same, and it is directed away from the charge plus q in an outwardly normal direction at each point. Therefore, we see that at each surface point, the electric field strength E is parallel to the area vector dA, which represents the area of an infinitesimally small elements on the surface. Since E is parallel to vector dA, the electric flux d phi passing through this local element is equal to E dot dA is equal to E dA cos 0, and as cos 0 is equal to 1, d phi is equal to E dA. Let us label it as equation 2. To find the total electric flux phi through the Gaussian surface, we now integrate d phi. Therefore, phi is equal to integral d phi, and this is equal into integral E dA. The total electric flux can also be referred to as the net electric flux. Since E is constant in magnitude for all points on the Gaussian surface, we have integral E dA is equal to E into integral dA. We know that to integrate dA is equal to A, which is the area of the Gaussian surface considered. Now, phi is equal to EA. We know that for a spherical surface, which is the Gaussian surface, in the present discussion, A is equal to 4 pi r square. Therefore, we have phi is equal to E into 4 pi r square. Let us label it as equation 3. Substituting equation 1 in equation 3 and simplifying, we get the net flux phi is equal to Q by epsilon naught. Let us label it as equation 4. We see that the net flux phi is proportional to the charge Q and closed by the Gaussian surface. Or we can say that the net flux is proportional to the charge inside the Gaussian surface. Now, consider two other closed surfaces, S2 and S3, around S1 of any arbitrary shape. We see that since S2 and S3 are closed surfaces, they can also be referred to as Gaussian surfaces. We have seen that the net electric flux phi through S1 is equal to Q by epsilon naught. By definition, electric flux is the number of electric field lines passing normal to a given area. Here, we observe that the number of electric field lines that pass through S1 also passed through S2 and S3, normal to their surfaces. Hence, the net flux through S2 and S3 is equal to net flux through S1. That is, phi is equal to Q by epsilon naught. Here, we observe that the net electric flux phi through any closed surface is independent of the shape of the closed surface. Hence, we conclude that the Gaussian surface can be of any arbitrary shape. Thus, Gauss' law states that the electric flux through any closed surface is proportional to the enclosed electric charge. That is, phi is equal to Qn by epsilon naught, where Qn is in the charge enclosed by the Gaussian surface. Let us label it as equation 5. Now, consider a point charge Q placed outside a closed surface. Here, we see that the number of field lines entering the closed area is equal to the number of field lines leaving it. Therefore, the net electric flux through the closed surface is 0, and it is important to note that the Gaussian surface, which is the closed surface, was not enclosing the point charge. In other words, the net flux through a closed surface not enclosing any charge is 0. Let us consider a cube of side L placed in the uniform electric field of strength E, directed along the x-axis. As the cube is the closed area and the number of field lines entering the cube is equal to the number of field lines leaving it from any of its surfaces, the net flux through the cube is 0. Now let's prove the same. For any surface of the cube of area A, which is normal to the electric field of strength E, the electric flux phi passing through it is equal to EA. Now we see the electric flux phi1 through face 1 is equal to minus EA, since it has inward flux. And through face 2, it is phi2, which is equal to plus EA, since the flux is outwardly normal to it. The flux through the faces 3, 4, 5, and 6, that is, phi3, phi4, phi5, and phi6, respectively, is equal to 0. Since the area of vector E is perpendicular to the direction of electric field with respect to these faces, therefore, the net electric flux through the cube is minus EA plus EA, which is again equal to 0.